This is SpaceTime Series 20, Episode 22. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime. Seems early galaxies were dominated by ordinary matter rather than dark matter. How ghostly neutrino particles could improve science's understanding of the universe. And how planet Earth probably began its planetary evolution with a solid shell rather than plate tectonics. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has found that early galaxies were dominated by ordinary matter, rather than the dark matter which dominates galaxies today. The findings, reported in 4 separate papers, including one published in the journal Nature, mean dark matter, which makes up about 80% of all the matter in the universe today, was far less influential in massive star-forming galaxies during the peak of galaxy formation 10 billion years ago. This is in stark contrast to present-day galaxies where the effects of dark matter appear to dominate. Scientists still don't know what dark matter actually is. The mysterious substance appears to be invisible. It can only be detected by its gravitational influence on so-called normal or baryonic matter. On the cosmic scale, we see normal matter as brightly shining stars, molecular gas clouds, and clouds of dust. Closer to home, it's the stuff that makes up the houses, trees, cars, the earth, dogs, cats, and even people. In contrast, dark matter doesn't appear to emit, absorb, or reflect light. It can only be detected by its gravitational effects. But we know dark matter is real because its presence explains why the outer parts of nearby spiral galaxies rotate more quickly than would be expected if only the normal matter we can see directly were present. The disk of a spiral galaxy rotates over a timescale of hundreds of millions of years. The central regions of these spiral galaxies have really high concentrations of stars. But the stellar density, the density of the bright matter, decreases towards their outskirts. Now, if a galaxy's mass consisted entirely of normal matter, then the sparser outer region should rotate far more slowly than the denser regions at the centre. But that's not what we see. Observations of nearby spiral galaxies show that their inner and outer regions are all rotating at about the same speed. Scientists call these flat rotation curves, and they indicate that spiral galaxies must contain huge amounts of unseen dark matter material in a halo surrounding the galactic disk. In order to study these flat rotation curves, astronomers used integral field spectrometers at the European Southern Observatory's VLT, or Very Large Telescope in Chile, to measure the rotation of 6 massive star-forming galaxies in the distant universe, each of them located at roughly the peak of galaxy formation about 10 billion years ago. It's the first time such a comprehensive study of the dynamics of a large number of galaxies has been carried out. And what the authors found was intriguing. The rotational velocities weren't constant, but actually decreased with radial distance from the galactic core. In other words, unlike spiral galaxies in the modern universe, such as the Milky Way or Andromeda, the outer regions of these distant galaxies were rotating more slowly than regions closer to the galactic core. And that suggests there's far less dark matter present than expected. The study's lead author, Reinhard Genzel from Germany's Max Planck Institute, says the findings suggest that dark matter was distributed differently in and around spiral galaxies in the early universe compared to its present-day distribution. Firstly, most of these early massive galaxies are strongly dominated by normal matter, with dark matter playing a much smaller role than in the local universe. Secondly, these early spirals were far more turbulent than the spiral galaxies we see in our own cosmic neighbourhood today. And both these effects appear to become more marked as astronomers look further and further back in time into the early universe. So, what's this all telling us? Well, it suggests that 3 to 4 billion years after the Big Bang, the gas in galaxies had already efficiently condensed into flat rotating disks. We can see that. But it also means that the dark matter halos surrounding these galaxies must have been far larger and much more spread out. Apparently, it took billions of years longer for dark matter to condense enough for its dominating effect to be seen in the rotational velocities of galaxy disks. This explanation is also consistent with observations showing that early galaxies were far more gas-rich and compact than what galaxies are today. The 6 galaxies mapped in this study were among a larger sample of 100 more distant star-forming spiral galaxies imaged by the VLT. 2 additional studies of some 240 star-forming spiral galaxies have also supported these findings. The detailed modelling shows that while normal matter typically accounts for about half the total mass of all galaxies on average, it completely dominates the dynamics of galaxies in the early universe. You're listening to Space Time. I'm Stuart Gary. A new study claims one type of neutrino may comprise exactly equal amounts of 2 other types of neutrinos. The findings by physicists and astronomers working with the IceCube Neutrino Observatory at the South Pole could help scientists better understand the universe. Neutrinos are among the most common particles in the cosmos. Huge numbers of these ghostly particles are generated through radioactive decay, nuclear fusion inside stars, in nuclear reactors, and from supernova explosions occurring as stars die. However, while plentiful, these elemental subatomic particles are also extremely weakly interacting with all other matter. In fact, right now, there are trillions of them passing through your hand, and you don't even notice them because they're so small and so weakly interactive. They're often described as the most tiny quantity of reality ever imagined. And that makes them difficult to study. Scientists don't really know what role neutrinos play in the universe because they're so hard to measure. They're thought to be similar in many ways to electrons, but unlike electrons, neutrinos don't carry an electrical charge. They also have at least 1 million times less mass than any other elemental particle, except for photons, which have no mass at all. In fact, neutrino masses are so small, scientists have not yet been able to measure them accurately. And worse still, neutrinos constantly change their properties, oscillating between 3 known types or flavors: the electron neutrino, the muon neutrino, and the tau neutrino. The new measurements of neutrino oscillations as they change from one type to another while they travel could shed some light on outstanding questions regarding the fundamental properties of these ghost-like particles. They could even help fill some key gaps in the standard model of particle physics, the foundation stone which describes the behaviour of fundamental particles and consequently the structure of the universe. However, while the standard model has a lot going for it, there are still a lot of things which it doesn't explain. There's no place in the standard model for explaining the nature of dark matter, the nature of dark energy, or for that matter, why our universe is filled with matter rather than antimatter, when equal amounts of both were created in the Big Bang 13.8 billion years ago. One of the study's authors, Associate Professor Thijs de Jong from Michigan State University, says the new research could help to better measure some of the properties of neutrinos, such as their masses, and how they morph or oscillate from one flavour to another. And in turn, that could help scientists answer some of the outstanding issues of the standard model. For a long time, physicists were hoping that discovery of the Higgs boson, the particle which gives mass to all other particles through an all-pervasive Higgs field, would point them in the direction of new physics beyond the standard model, maybe eventually explaining things like dark matter and dark energy. De Jong says that unfortunately measurements of the Higgs haven't really turned up many clues, so he's hoping he may find something new by studying neutrinos. IceCube can detect neutrinos with a far wider range of energies and distances than other experiments, allowing scientists to cast a wide net. Energetic neutrinos produced by cosmic rays hitting the Earth's atmosphere can be detected at the South Pole using Antarctic ice as a giant particle detector. It uses 1 billion tons of Antarctic ice cap beneath the US Amundsen Scott South Pole Station to observe them. It's operated by a collaboration of some 300 physicists and astronomers from 48 universities and national laboratories across 12 countries. If one neutrino is a precisely equal mix of 2 flavours, it could be a surprising coincidence, or there might be a deeper reason for it, coming from new physics beyond the standard model. The new measurements are consistent with results from other experiments using neutrinos with lower energies. But whether this flavour mixture is exactly balanced is still unclear, and consequently further observations will be needed in order to enable these measurements to be made with a far higher degree of precision. I'm Stuart Gary. This is SpaceTime. new study claims planet Earth probably began as a single solid shell, which broke apart later to form the planet's characteristic individual tectonic plates. The findings, reported in the journal Nature, could help settle a long-standing debate about the origins of tectonic plate activity on Earth. Today's Earth is a dynamic planet, with an outer layer composed of giant tectonic plates that grind together, sliding past or dipping beneath one another, giving rise to earthquakes and volcanoes. Others separated undersea ridges where molten rock spreads out from the centres of major ocean basins. But the new research suggests that this wasn't always the case. Instead, shortly after the Earth formed and began to cool 4.6 billion years ago, the planet's first outer layer was a single solid but deformable shell. It was only later that the shell began to fold and crack more widely, giving rise to modern-day plate tectonics. The research is the latest salvo in an ongoing debate across the geological research community about whether plate tectonics began as soon as the planet cooled enough to develop a surface crust, a theory known as uniformitarianism, or whether the Earth first went through a long phase with a solid shell covering the entire planet, an hypothesis known as the stagnant lid model. These new results suggest that the stagnant lid or solid shell model is closest to what really happened. To reach their conclusions, the authors studied rocks collected from the East Pilbara terrain, a large area of ancient granitic rock located in the north of outback Western Australia. These rocks are among the oldest known, ranging from about 3.5 to 2.5 billion years of age. The researchers specifically selected granites with a chemical composition usually associated with volcanic arcs, a telltale sign of plate tectonic activity. The authors looked at basaltic rocks from a region known as the Associated Kukal Formation. Basalt's the rock produced when volcanoes erupt, but it also forms the ocean floor as molten basalts erupt from spreading ridges in the centres of ocean basins. In modern-day plate tectonics, when ocean floor basalt reaches the continents, it dips or subducts beneath the Earth's surface, going back into the mantle. As it does so, it generates fluids that allow the overlying mantle to melt and eventually create large masses of granite beneath the surface. Previous research suggested that Kukal basalts could be the source rocks for the granites in the Pilbara terrain because of the similarities in their chemical composition. So the researchers of our study set out to verify this, but also to test another long-held assumption, namely whether the Kukal basalts could have melted to form granite in some way other than the subduction of the basalt beneath the Earth's surface. If so, it means that plate tectonics may not yet have been happening when the Pilbara granites formed. To find out, the authors performed thermodynamic calculations in order to determine the phase equilibria of average Kukal basalts. Phase equilibria is the precise description of how any substance behaves under various temperature and pressure conditions, including the temperature at which melting begins, the amount of melt produced, and its chemical composition. For example, one of the simplest phase equilibrium diagrams describes the behavior of water. At low temperatures and or high pressures, water forms solid ice, while at higher temperatures and lower pressures, water forms gaseous steam. It's why the boiling point of water decreases with higher altitude and why freezing cold water at the bottom of the ocean doesn't turn to ice. One of the study's authors, Professor Michael Brown from the University of Maryland, says if you take a rock off the shelf and melt it, you'll get a phase diagram, but you're stuck with a fixed chemical composition. But with thermodynamic modelling, you can change the composition, the pressure and the temperature all independently, thereby providing a far more flexible way to answer questions which simply can't be addressed through experiments on rocks. So, using the Kukal basalts and the Pilbara granites as a starting point, the authors constructed a series of modelling experiments to reflect what may have transpired in an ancient Earth without plate tectonics. And their results suggest that indeed Pilbara granites could well have formed from Kukal basalts. This transformation could have occurred in a pressure and temperature scenario consistent with a single shell covering the entire planet. Plate tectonics substantially affects the temperature and pressure of rocks within Earth's interior. When a slab of rock subducts under the Earth's surface, that rock starts off relatively cool, and it takes time to gain heat. And by the time it reaches a higher temperature, the rock's also reached a fairly significant depth within the mantle, which corresponds to high pressure. In the same way, a diver experiences greater pressure at greater water depth. In contrast, a stagnant lid regime would be very hot at relatively shallow depths and low pressures. Geologists refer to this as a high thermal gradient. The results suggest that the Pilbara granites were produced by the melting of Kukal basalts or similar materials in a high thermal gradient environment. The composition of the Kukal basalts also indicate that they, too, come from an earlier generation of source rocks. The authors therefore conclude that a multi-stage process produced the Earth's first continents in a stagnant lid scenario before plate tectonics began. The study's lead author, Dr. Tim Johnson from Curtin University, says the study shows that understanding the ancient past by looking at what's happening today may not always provide an accurate picture of historic geological processes.
Almost all the large-scale geological processes we can see today, things like volcanoes and earthquakes, the formation of mid-ocean ridges, mountain building, these sorts of things are the result of plate tectonics. So that's the idea, really, that the brittle outer shell of the Earth is subdivided into broken fragments. So like a hitting a creme brulee with a teaspoon or breaking an egg.
That's very unusual, isn't it, in terms of planets in our solar system? When you look at somewhere like Venus, it has a very soft outer crust, we think it does, and there's no evidence of plate tectonics. Mars is much smaller, but it also has no evidence of plate tectonics.
Sure.
And so,
that's right.
Yeah, our Earth is a little unusual in that regard.
That's right. So one of the precepts of geology, really, one of the founding ideas of geology is this so-called uniformitarianism, where these processes that we can observe today, these plate tectonic processes, these slow processes, have been operating throughout the entirety of Earth's history. So we can understand the ancient past by looking at things that are happening today. And our research has suggested this may not be true when you look at the very early Earth, around 3.5 billion years or older.
How did you do the research?
So we were looking at a combination of rocks. There's two main rock types that you find in the Pilbara. There's these ancient granitic rocks, which are called TTGs, a rather technical term, it doesn't really matter. And there are dark, so they're quite pale in colour rocks, and there's these dark green or grey basaltic rocks. So basalts are volcanic rocks that come out of things like Hawaii and Iceland and things like that, and erupt onto the ocean floor to form new oceanic crust. Now, the granites, these so-called TGGs, have chemistries, compositions of particular trace elements that suggest that have similarities with modern-day granites. And on the modern Earth, granites form basically when these plates I was talking about dive beneath one another, or one dives beneath another. As it gets down into the deep Earth, it starts to melt and it produces granites. And these ancient granites have got compositions which are similar to that. And that's led some people to believe that plate tectonics operated in the very earliest stages of the Earth. So we've basically looked at trying to model what happens to these basaltic rocks, which have been proposed by other people to be the source rocks for these granites. So you melt those to produce the granites, whether we can produce those ancient granites in a different geotectonic environment. And it turns out that we can. So rather than there being plate tectonic environment where we had lots of rigid plates, as you were alluding to earlier, the Earth might have been a little bit more like Venus, where you had a single, soft, deformable, thick outer shell before it started breaking up into individual plates.
What would cause the surface to harden and form the tectonic plates we now see? Is it simply that temperatures cool down enough on the surface to allow that to happen? Whereas on Venus, we still have these really hot temperatures.
No, exactly so, yes. So it's so-called secular cooling, yes. So as you cool, things become more rigid, more brittle, and the new crust that you produce at mid-ocean ridges becomes thinner because the mantle underneath the layer, underneath the crust, is much cooler, so it melts less and produces a less thick layer. Yeah, so that's exactly the driving force, is temperature, and the Earth would have been much hotter in its early life, and you would predict that things would have behaved differently, and our research supports that.
You've been able to do that under laboratory conditions, so you had extra variabilities you could include rather than simply the chemical of the individual rocks you're looking at.
Yeah, that's exactly right. So as you say, you could take a block of ice, and if you sit on it or apply a lot of pressure to that without changing the temperature, you will find that ice melts. So rocks behave in a predictable way. They're much more complicated than ice. They've got lots more different elements in them and different minerals. But there's various bits of software and clever people have put models together to allow us to predict how minerals, solid minerals, and how melts behave under changing conditions. And we're mainly talking about changing pressure, which is a proxy for changing depth. So as you go down in the Earth, the pressure gets higher, and changing temperature. So it's using these clever models that we can input a style starting composition, so the ingredients of these basalts that we think were the source compositions, the parents, if you like, of these granites, and then we can predict how they would behave under certain pressure temperature conditions. And our results suggest that these geothermal gradients, so the increase in temperature with depth, would have been much higher than we associate with normal subduction zones, which is where these plates collide in a modern Earth.
So has this ended the debate over which came first?
Definitely not, no. Nothing is ever black and white in science, and the Earth is a very complicated system, and we're certainly not saying that subduction could not have been happening at some places on the planet throughout Earth history. I personally think, or we think, that the dominant mechanism of how the Earth's surface behaved in the early Earth was different to how it does today, but there wasn't one, 2:30 on a Wednesday afternoon, plate tectonics started. That certainly isn't the case. So no, it certainly isn't a definitive answer, but I think it's strong evidence in support of a non-uniformitarian, a non-plate tectonic view of the early Earth.
That's Dr. Tim Johnson from Curtin University. You're listening to Space Time. I'm Stuart Gary. The SpaceX CRS-10 Dragon cargo ship has splashed down safely in the North Pacific Ocean off the California coast, some 320 kilometres southwest of Long Beach. The capsule was loaded with some 2.5 tons of experiments and equipment being returned to Earth from the International Space Station. The Dragon CRS-10 had been docked to the orbiting outpost for a month. Dragon was undocked from the space station's Harmony module on Saturday by crew using the station's robotic arm to manoeuvre the capsule to a safe parking position about 10 metres from the station. After being released the following day, the Dragon carried out a series of 3 departure burns to move it safely away from the space station. 5 hours later, Dragon undertook a 10-minute deorbit burn using its Draco thrusters to slow the spacecraft down and causing it to begin falling out of orbit. The Dragon service module, or trunk as SpaceX like to call it, was then jettisoned and allowed to burn up on re-entry. The Dragon capsule, meanwhile, began atmospheric entry interface protected by its re-entry heat shield. Following the premature retirement of the Space Shuttle fleet, Dragon provides the only means of safely returning equipment and experiments to the Earth's surface, other than the Russian Soyuz capsules, which are used for crew return and therefore have very little cargo carrying capacity. Once Dragon splashed down, SpaceX recovery team successfully retrieved the capsule from the ocean. Time-sensitive experiments were then removed before the spacecraft was transported to Texas, where the rest of the cargo will be unloaded. This is Space Time. I'm Stuart Gary. Staying with SpaceX and following an earlier delay due to high winds, SpaceX has successfully launched the new telecommunications satellite into orbit. The spectacular nighttime launch from Space Launch Complex 39A at the Kennedy Space Center in Florida was the 3rd Falcon 9 launch this year and the 2nd off the historic former Space Shuttle and Saturn V Apollo Moon rocket launch pad.
T-minus 30.
All gas goals as complete.
T-minus 20.
Stage 1 tanks pressing for flight.
T-minus 10. 9. 8. 7. 6. 5. 4. 3. 2. 1. 0.
Vac engine shell has begun.
First stage separation has moved. Bearings have confirmed.
The Falcon 9 core stage burned for over 2 minutes and 40 seconds before MECO, or main engine cutoff, and stage separation. The upper stage then ignited for the first of 2 engine burns, which eventually placed the EchoStar 23 satellite into a geostationary transfer orbit 27 minutes and 19 seconds after launch. The 5,500 kilogram EchoStar 23 is the most massive satellite yet launched by the Falcon 9 into a geostationary transfer orbit. In fact, the mission required the maximum fuel burn for the Falcon 9. That meant the launch vehicle flew in a fully expendable configuration. In other words, there was no plan for a powered return of the core stage for reuse, a feature of most recent Falcon 9 launches. The fully expendable configuration also meant the manoeuvring grid fins and landing gear usually fitted to the Falcon 9 were also omitted from the core stage of this flight. Built by Space Systems Lorel, the EchoStar 23 telecommunications satellite uses an SSL 1300 bus originally intended for use on another EchoStar spacecraft to provide additional capacity for the 2008 Beijing Olympics. That mission was eventually scrapped due to delays in getting the satellite ready in time. SpaceX's next mission, slated for March the 27th, will be the first use of a refurbished Falcon 9 core stage recovered from a previous flight. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.
SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.